Right. In Chapter 2, we're going to talk a lot about the idea of logical reasoning. So we're going to use this by talking about the idea of patterns, finding missing terms, inductive reasoning, deductive reasoning, so on and so forth. So the first few sections of the chapter are going to deal with a lot of writing. Okay, a little bit less with the numbers. But then we're going to add the concept of algebra later on as we get going with it. So to start, I have a picture here of, a red square, 3 orange, and 6 yellow. And so the concept is to figure out what is next. Well, what comes next is we should have a block of 4 squares, and then 3 squares, and then 2 squares, and then 1 square. So things that we can add onto this as well. Number 1 is we could talk about color. So one of the things that some people notice is that maybe this one should be green, because if you think about the colors of the rainbow. So you probably learned at some point, red, orange, yellow, green, blue. Other things to notice out of this is that there's 1 square, then there's 3 squares, and then there's 6 squares, then there's 10. So notice that it's going up by 2, then it's going up by 3, then it's going up by 4. So if we were to make a prediction, the next one would have 15 squares because it would go up by 5. Okay? All right, example number 2 deals with the concept of these kind of slices of pie or slices of pizza, however you want to look at it. And to figure out what would be next is, well, it looks like we've got 2, then we've got 4, then we've got 6. So I would say that the next amount would have 8. And in each of our cases, only one of the square or slices of pie is colored blue, so that's what it should look like. Again, adding on to this, notice that 1/2 is shaded, 1/4 is shaded, 1/6 is shaded, 1/8 is shaded. So the denominator keeps going up by 2. A couple more examples. All right, and number 3, what we want to do is we want to try and find a pattern in the numbers, and it has to be consistent for all of them. So it looks like we're subtracting 3, subtracting 3, adding 3, adding 3, adding 3. So therefore the next number would be 7, and our rule is going to be that we would be adding 3 each time. In the next one, we got 1, 4, 9, 16. So we want to try and notice that the next one would be 25, and the reason is that we have perfect squares. Number 5, for this one, we got 1, 2, 3, 5, 7, 11, and 13. This one's a little bit trickier. The next number is actually going to be 17. A lot of people think it's 15. But what we're supposed to notice that these are all prime numbers. Numbers that are divisible by 1 in itself. Number 6. This is Fibonacci's sequence. So 1, 1, 2, 3, 5, 8. What's happening here is that the first 2 numbers add together to be the next number, and then 1 and 2 add together to be the 3, and then the 2 and 3 add together to be the 5, and then it just keeps going. So that means 21 and 34 are going to add together to be 55. Okay. All right, so a conjecture. A conjecture is basically a statement or a conclusion. It's an observation, okay? So let's say that it is an observation. So our conjecture, okay, for like the ones above would be like, oh, we're adding 3 each time, or it's the perfect squares, or it's the prime numbers. That's our observation, okay, that we're drawing that conclusion. Okay, so after observing, for numbers of years, okay, the sum of 2 odd numbers, what happens when 2 odd numbers add together? Like 5 plus 3, 7 plus 9. Well, you always get an even number. So the sum of 2 odd integers is even is your conjecture. Okay, the product of an even positive integer and an odd positive integer. So like 7 times 8, Or 3 times 2. What happens when you multiply an even and odd? Well, again, you always get even. So the conjecture is that the product of an even positive integer and an odd positive integer is even. All right, next page. Reasoning. Inductive reasoning. Inductive reasoning is kind of like your conjecture, and it is simply that you are drawing a conclusion based upon observable data. So you are watching something, or you see something, or you look at a pattern, and then you draw a conclusion based upon it. Okay? So that's inductive reasoning. Whereas deductive reasoning is the idea of a hypothesis. And that's where you're kind of making a prediction before you try an experiment. So it's kind of like the inductive is like after, and the deductive is kind of like before, to put it in simple terms. All right, in example 7, okay, conjectures. We're given 5 points. We're supposed to make a conjecture about the number of ways to connect the different pairs of points. So if I had 1 point, how many connections can I make? None. If I had 2 points, how many connections can I make? Well, I can make 1. If I had 3 points, and it says they have to be collinear, so 1, 2, 3, okay, well, I can make 1, 2 connections. Okay, if I had 4 points that were, again, collinear, I would be able to make 3 connections, 1, 2, 3. And then if I had 5 points, 1, 2, 3, 4, 5, I'm going to be able to make 4 connections. Okay, so your conjecture is, helping you maybe make a prediction about how many connections are there going to be if there were 6 points or 10 points or 12 points. And somebody might say, oh, well, the number of connections is always 1 less than the number of points. So notice that, 1 minus 1 is 0, 2 minus 1, 3 minus 1, 4 minus 1, 5 minus 1, okay? So that could be like your conjecture. All right, a counterexample is basically an example. Doesn't have to be a statement. It's just something that, makes it false. Okay, so we're actually going to start with the bottom one. Might be a little easier. Okay, if an animal has spots, then it is a leopard. Well, all you have to do is think of an animal that has spots that is not a leopard. So like someone might say a cheetah. Somebody else might say a Dalmatian. These are all examples, or what we're going to say as counterexamples, examples that make the statement false. So on the one above it, all quadrilaterals are equilateral. So we learned in the last chapter quadrilaterals are 4-sided figures. Equilateral, all 4 sides are equal. So now all we have to do is come up with a quadrilateral in which not all 4 sides are equal, like a trapezoid. That will never happen. Okay, so that would be your counterexample. Okay, the last one, the tricky one. For all real numbers x, 2x is greater than x. So what it's saying is that, like, if, let's say, x is equal to 5, that 2 times 5 is greater than 5, okay? And that's going to be true, right? So what would make it not work? Well, what if we made it negative 5? So 2 times negative 5 is negative 10. Negative 10 is not greater than 5. So that would be your counterexample. Your counterexample would be x is equal to negative 5. Okay? All right, we are going to do the function rule because there is one like that on the homework. And the idea here is what we want to do is we want to write our equation in slope-intercept form. So our goal is to come up with y equals mx plus b. All right, so reminders. M is equal to your rise over your run. You've probably heard that before. Or your change in y over your change in x. Okay? Well, if I look at the change, it looks as though my y values are going up by 2 and up by 2. my x values are going up by 1 and up by 1. So my change in y is 2, and my change in x is 1, so that means m is equal to 2 over 1, or 2. The b is when the x value is 0, and the y value becomes the y-intercept. So if we stick with our idea of a pattern, 3, 2, 1, 0, and then our y value simply becomes 6, 4, 2, and 0. And so now, in our case, we've got 0, 0. So what that means is b equals 0. If I were to put these two things together, we would end up with y equal to 2x plus 0, but you don't have to write y equal to 2x plus 0. You could just write y equal to 2x. All right, if you got questions, come with them tomorrow.